Hi guys, welcome to our first video in chapter 4, the structure of the atom. And we're going to begin our discussion of the structure of the atom with section 4.1, early theories of the atom. And our question that we want to think of for this entire unit, and I would write this down in your notebook, is what makes up matter? So we're really looking at the fundamental building blocks of matter. What does it look like? And so for our early theories of the atom, we're actually going to start way back in ancient Greece, about 2000 years ago, maybe more. About 400 BC, this happened. And there were two prevailing theories. The first one was continuous matter theory. And this is the concept that there's not a smallest piece of matter. You can cut the matter in half and there's never a limit. And this was actually the theory that won out from the ancient Greeks. And this was what was considered scientifically relevant for all of ancient Greek history, Roman history, the Middle Ages, all the way up to the 1800s. And so I have on the right-hand side here what the model of the atom is going to look like. And so for continuous matter theory, I'm actually just going to draw one of those, an infinity sign. That means there's an infinite, matter never has the smallest particle. It just keeps getting, you can go smaller and smaller with no limit. Of course, competing with that was atomic theory. The word atomos actually being Greek for indivisible. And atomic theory was proposed by Democritus, and it stated that all matter is composed of tiny indivisible particles called atoms. Remember, that means indivisible in Greek. Now, Democritus, however you say his name, he was not the winner of this debate here. And unfortunately, continuous matter theory won out over atomic theory all the way until way back, way further future. I should put the date here for Dalton's model of the atom. This is in I think it was like 1803 or something, but we can write just 1800s. So for the transition from some erroneous theory of matter to Dalton's model of the atom, this took about 2,300 years or so to get from one to the other. So this is kind of a long time of thinking of the long thing. Or the wrong thing. Anyway, so John Dalton was a scientist in the 1800s, and he realized that continuous matter theory could not explain why certain things happened. Specifically, Dalton was looking at chemical reactions and the ratios of chemicals involved in those reactions. And he said, basically, continuous matter has no explanation for this. Instead, we got to look at atomic theory, which happened to be correct. And so over here on the opposite side, I have Dalton's model of the atom. So right here, we can see what Dalton's model of the atom looks like. And this one is very simple. It is a tiny indivisible sphere. I wrote homogeneous next to it. That means that there's no details in this. You can see it's just a circle. Imagine a tiny marble. So for Dalton's theory, we're going to think about a little marble, and the different elements, like your oxygen versus your carbon, have different characteristics because they have different sizes. It's not due to anything except the different sizes of the elements. So again, Dalton's model of the atom has matter as tiny indivisible little spheres. Well, this was better than continuous matter theory, but another 100 years later, so look at this jump. We go 2,300 years to go from one theory to the next, and then only a mere 100 years to get from Dalton to J.J. Thomson's plum pudding model. Well, J.J. Thomson noticed that atoms are actually affected by charges. He did this by firing some charged particles out of what's called a cathode tube, right? So cathode tube shoots charged particles at atoms, and he noticed that atoms were affected by these charged particles from the cathode tube. This indicated to him that atoms have some charged I said the word element. I'm going to change element to some charged component. Element has a pretty specific definition in chemistry. So if the atoms are interacting with charges, that means they must have some kind of charge themselves. So he proposed what's known as the plum pudding model. And I have that picture right here to the right. And you can see in this picture, imagine plum pudding. This is, I guess, an English dessert that apparently looks like a pudding with raisins in it. And I think that's great. But to me, this looks like a chocolate chip cookie. So I'm okay if we want to call this a cookie model of the atom. And in this model, you have a positive charged background. So in this, all of the gray, imagine as being positively charged. And then within that positively charged substrate, you have some negative charged electrons just embedded throughout. So that gives the charge that Thomson noticed. So again, this is a better model than Dalton's model. This now has some charged aspect, which is very important because atoms are charged and have a lot of charged particles, which do things. But it didn't explain everything, especially concerning Rutherford's experiment. So the next three models are the most important ones. These are the ones that really matter the most. And Ernest Rutherford, by the way, came up with what's called the nuclear model. And I have this pictured here. And this is starting to look a little bit more like what we maybe think of an atom as. In fact, this may be what you think of an atom as. This is a bad representation of an atom. We'll talk about why right now. So this was only 6 years after Thomson theorized the plum pudding model. Rutherford tries to prove this. And so what he did, if you look at this image here, like if you look at this cookie, you can see that it's mostly filled. It's almost entirely a space-filled model, whereas the next one's pretty empty. Well, Rutherford came to the conclusion that the atom was mostly empty space by firing, here's what he said. He shot a bunch of radiation at a piece of gold foil, which kind of looks like aluminum foil, but it's made out of gold. So you can imagine it's very expensive. Rutherford found some shocking results. He actually found, he expected that most radiation would would bounce off the atom and be scattered by this solid substrate. So we can write expected, let's say expected most radiation to pass through, to bounce off from the atom. He found that 99.5% of the radiation passed straight through, undeflected, indicating that it ran into nothing. And this was pretty shocking considering he thought the atom was mostly full. And then some even more shocking results were that 0.5% of the time the radiation did hit something, but about 0.01% of the time the radiation bounced straight back at him. Now, I know you guys aren't at him, quote unquote, right? I mean straight back at the quote unquote gun firing radiation at the piece, right? It didn't actually hit him, which is why he stayed alive, right? He didn't die of radiation poisoning. So this is probably not too crazy for you guys because I understand that you maybe don't understand atomic radiation that well. But here's how Rutherford explained his results. So Rutherford is quoted as saying, this was equivalent to firing a shotgun at a tissue and having the bullet bounce back, which imagine, hopefully that is a little more salient of an example to show you that there's something unexpected happening here. And Rutherford was able to conclude that, okay, if most of the radiation is passing straight through the atom and it's unaffected, then the atom must be mostly blank, mostly empty space. And so conclusions, and these are really important conclusions. The atom is mostly empty space. That is very important, mostly empty space. He also found that although most of the atom is empty space, there was that one really dense part that reflected the radiation back at him and that really deflected things very strongly. And so he was able to conclude that the mass of the atom must be concentrated in a very small location. So Rutherford concluded that 99.9% of the mass of an atom resides in the nucleus. So if the atom was, I don't know, a classroom, imagine the entire classroom is the volume of the atom. It's all empty, and all of the mass of your atom would be in something about the size of a raisin in the middle of the room. So that's where all the mass is. It's kind of a weird conclusion, but these two things we actually found out to be correct. So those two things are true. Now, again, as happens in science, we did a little bit more investigation and we found out that this isn't the whole story. In fact, we have two more iterations of the atom to talk about. Now, Niels Bohr in 1913, he realized that the nuclear model didn't explain why neon lights could produce light and why every element actually has its own unique emission when you pass electricity through it. We'll do some examples around this in class. But Bohr came up with what's called the Bohr model, also known as the planetary model. And I want you to definitely pay attention here because this is our most useful model of the atom. This is it. This is what we should think of. I know there's another one, but it's quantum mechanics, and you know it's complex. So we are going to focus on our Bohr model as being our most important model of the atom. And this is where we're going to learn actually a lot of our quantum mechanics and a lot of our chemical reaction principles. So I want you to visualize atoms this way. And in this model, you've got your nucleus in the middle. Of course, that's where almost all of the mass of the atom is. And then you have your electrons on these rings. These rings are called orbitals. I'll write that out. These rings are called orbitals. And they are areas where electrons exist. We're going to learn how many electrons go on each ring. How do we know how many rings there are? All that good stuff in subsequent lessons. But this is going to be our main visualization of what an atom looks like. And it's similar to the nuclear model in that it has a nucleus and it has electrons around it. But here we've added a detail that those electrons and those orbitals occupy discrete energy levels. Orbitals, and we could say, I'll type this out, but let's write out electrons in distinct energy levels, which is a way to explain why neon lights are able to emit energy. Okay, so that's our Bohr model. We'll draw them, we'll practice them. It's going to be good. Next, our quantum mechanical model. And finally, the last model of the atom. Our quantum mechanical atom model was developed by Erwin Schrödinger. If you've ever heard of Schrödinger's cat, we can talk about it in class. It's pretty famous. In 1926. This is our currently accepted model of the atom. That does not necessarily mean we won't update it in the future, but it does mean that this is what all of our evidence points to as the correct description of an atom. And here the key differences, if you notice, all of these have a nucleus. The nucleus in the nuclear, Bohr, and quantum model are all identical. It's where the electrons are that we're really adjusting. And we went from electrons just in undescribed rings to electrons in specific energy levels called orbitals. And now we are going to keep the term orbitals, right? Electrons are still in orbitals, but here those orbitals aren't just rings. They are instead called an electron cloud. So in a quantum mechanical model of the atom, electrons exist in an electron cloud, and that cloud describes an area of high probability for finding an electron. We can talk about why when we get to our unit on quantum mechanics. We will go more into this. By the way, quantum model, this is also called the wave mechanical model. That sometimes comes up on the regions. But again, according to the wave mechanical model, your electrons are in an electron cloud. That electron cloud has different shapes based on how big the atom is. And as I said before, we'll talk more about that in our unit on quantum and electron counting. I think it's unit 6. But just remember for quantum that your electron cloud is an area of high probability for finding electron. So if we look at this circle here, this picture, imagine where the shading is a little bit darker. That is an area of very high probability for finding a certain electron. And the area that's lighter shaded, well, that's an area of high probability for finding another electron. All right, guys, that's it for this video. I will see you guys in the next one. Bye.